So remember in grade 12, back in grade 12 pre-cal last semester, we graphed polynomial functions and we looked for x-intercepts, y-intercepts, and the direction of the opening, like if it's an odd function, if it's an even function, if it's a negative coefficient, positive coefficient. So all those things still apply, but now we're going to look at the humps and the valleys of this and how far they go. So there's two different sets. We have absolute maximums and absolute minimums, and they are exactly what they say. It's a continuous function, and if it's an absolute maximum, that's the highest the graph goes. So let's say our derivative was a parabola, and it opened down. This would be an absolute maximum, because the graph, no values on the graph ever go above that. But let's say we had a cubic function that did something like this. The absolute maximum would be that infinity piece here, right? But we would have a relative maximum right there. So that's like in this area, what's the maximum value? So relative is in so when we talk about relative max and mins, in the relative, it's like over a particular domain. Like, yeah, my graph, if we did the domain of this cubic function, it would be negative infinity to positive infinity. But if I said, what's the relative max on the domain 0 to 5, you'd have to find the highest y value. So when we're talking about maximums or minimums, we're talking about y values. And if you haven't guessed it already, calculus is all about like what is y doing. Grade 12, grade 11, we looked at what x was doing. Calculus, we're looking at what y is doing.
So pre-cal, we just wanted to find our x, and now we accepted that it's our x. Now we just want to know y.
Exactly. Okay, so if we look at this graph, we're going to, just looking at the graph, we're going to determine the absolute maximum, absolute minimum, relative maximum, and relative minimum. Okay, so let's do, what do I want to do? I don't want to start. Okay, so, and notice my increments are different. They don't tell me what my increments are. They've labeled the x value A, B, and C, and we're just kind of looking at those points right there. So when we look at when x is A, so we're looking at this point right here. Is that a relative max, a relative min, an absolute max, or an absolute min?
Relative min?
It's a relative max. Okay, the reason why I know it's not an absolute max is because I have a point higher. But we do know that at that particular point, that is a relative max. Okay. At x equals b. So now we're looking at this point. When we're looking at this point, what's that one?
Which one?
The b, at the b.
Relative min?
It's a relative min. How come it's not an absolute min?
Because it's a point below it.
Because these continue on forever, right? So we know our minimum is going to be like that negative infinity. It goes on forever. So this is a relative minimum. At x equals c, so now we're looking at this point here.
Absolute max?
It's the absolute max. It's the highest point the graph is going to go. And so in this case, we would all agree that this goes on to negative infinity. So what we would say is that there is no absolute minimum. because it goes to negative infinity, and negative infinity is, it's a concept, it's not an actual point. So in this case, we say like, there is no absolute minimum, because I can't pinpoint the point of minimum. So we just say that there's none. Okay, so that's that. Easy peasy. Okay, so we're going to talk about increasing and decreasing just over a domain interval. So what is the y value doing? And we're going to talk about, is the graph, like we're just, again, you guys have seen all this stuff, none of this is new, but we're just talking about it in kind of a different way. So if we're looking at increasing and decreasing, we're looking at, as you travel through the domain, what's happening to the y's. Are they getting bigger or are they getting smaller? So you're looking at what's happening through a domain value, and y's are getting bigger. For increasing, we've talked about increasing and decreasing functions before, and now we're going to break it down on one graph. We're going to talk about intervals that increase and decrease. And these are related to, so this is the exact same graph we had before. So, I mean, I don't think you guys need to copy that down. I just think that, just keep that in mind. We're looking at what the y's are doing. What's happening over this? So we're looking at some key points. This is the exact same graph from the other page. We said that this was a relative max, a relative min, and an absolute max, right? So relative max, relative min, and an absolute max. That's what we decided on the last page. So now we're just going to look at, kind of break our graph down. I don't know if I have enough highlighters, but I will do my best. Ooh. I think this will work. So we're going to look at the graph in different pieces. We're going to look at that as it hits the relative maximum. Then we're going to look at it from the relative maximum to the relative minimum. Whew, I went to the median. Then we're going to start at the relative minimum and head to the absolute max. And then we go from the absolute max down. You don't need the colors, but just so you know, kind of, it's broken up by those absolute and relative points. So if I want to make a domain statement about the purple part of the graph, what would that be? I'm looking for a domain statement for the purple part of the graph. A, right? So this is purple. This is the purple section of the graph. So what's happening? Are my y values getting smaller or are they getting bigger as I travel from left to right? They're getting bigger. So we would say that on this interval, the y values are increasing. Okay, so now we're going to do domain statement. Now notice I didn't include A in my domain set. Anybody know why? It's that static point. We've defined it as it's a relative max. So it's neither increasing or decreasing there. Exactly. It's kind of like a zero of a function. Yeah. So that's why this is not including. So now we're looking at the green section. And if I do a domain statement here, I'm going to go from A and I'm heading to B. Heading from, oh, that's a really dark highlighter. A to B. So as I move again, left to right, as I'm moving from left to right, what are my y values doing? they're decreasing. So none of this, like, I mean, you can look at the graph and I think you're all pretty confident in knowing if the graph is going up or going down, because that's really what we're looking at. So in the orange piece, I'm going from B to C, and again, non-inclusive of those points. And I'm going always traveling left to right, and I would be increasing. And then on my yellow section, I'm going C to positive infinity, because that keeps going on forever. And my Y values, oops, are decreasing. Just because I want my notes to look pretty, I'm just going to make sure everything's highlighted as it should be.
Why don't you just use like pencil?
Now, you could break it, oh, sorry. You could break it down like this, like you can break it down so that it is broken down into these points, but oftentimes you'll see it written as increasing as a single statement. So increasing happens from negative infinity to A in unison with B to C. Right? So it can be written like this. There's nothing wrong with writing it like this, but this is more likely how you're going to see it. And then decreasing, should have left myself more room. Decreasing is going to be from A to B in unison with C to infinity. So it's more likely you'll see it like this. That's probably more mathematically correct, grammatically correct to write it like that. But there's nothing wrong with this if this helps your brain. But please note when you're putting it in this way, you always want your lower stuff, your furthest left-hand stuff, to come first in these sets. Like I wouldn't put C to infinity in unison with A to B, because then they're in the reverse order. Okay, and you guys know this. Go back to grade 10 when we're doing linear functions. If you have a line that's rising to the right, so if you have a graph that's rising, ooh, you guys can't see that, sorry. You have a graph that's rising to the right, I know that that line will have a positive slope. And if I have a graph that's falling to the right, that would be a negative slope. And so we know that the slope of a function at a point of tangency or a specific point is that first level derivative, right? So we know a little bit about what's happening if I were to lay, I don't have a ruler, now I have a ruler, like if I made this my point of tangency and I did my tangent line here, if we found the slope of this line and we found it to be negative, we know that our graph would be decreasing here. So we're tying what we learned about derivatives to actually applying it to here. We can know something about the graphs without ever really having to graph them. Okay, here's some funky pictures that sometimes we don't always think about. Increasing, again, we're looking left to right, and the curve, all that's happening is the Y values. So you can curve over or you can curve under, but really what we're looking at is our Y values to be increasing. And we're going from point A to point B. So we're traveling left to right, and our Y values are increasing. It doesn't matter if it scoops over or scoops under, there's still an increasing interval. And the opposite is true. So if you have a negative slope, you're going to find that your values of Y are decreasing. Again, it doesn't matter if it scoops over or scoops under, the Y values are decreasing. You good, Rahat? Okay. All right, let's look at the slopes. Let's see how good you are at this. Can you determine the equation of the slope at the point of tangencies? all you have to do is find the first level derivative, right? So if we find g prime of x, we know that that's negative 2x minus 2. So that would be my formula for slope. Now, if you look really closely on this, it's already figured out what all these things are. So at negative 2, my slope is a positive 2. At 1.5, my slope is a positive 1. They're already calculated for us here. If I'm at 1.1,
That's where we check it in the formula.
that's when we're going to chuck it in the formula.
Negative 1 is going to be 0.
Well, let's fill out the ones that are listed on the chart here. And then at negative 0.5, it's 1. And at 0, it's a negative 1. And that's a negative 2. So we only have to calculate 2. So we're going to use
.2.
Is it 0.2? Is it positive?
No, yeah, positive.
Positive?
I'm positive.
You're positive it's positive? And this one's going to be
Negative 0.2.
negative 0.2. And we would expect that because as we travel to where the slope is 0, these y values are increasing. So my slopes will be positive. And as we travel this direction, my y values are going down, so my slopes should be negative. So there's that link between slopes and the increasing and decreasing. And you probably already knew that, but we're looking at it really specifically now, and we're using our first derivative to solve for, which we've never had before. Fermat's theorem. I have a whole book on this. I don't know if it's here or at home. I might have a whole book on Fermat's theorem. I think it might be up there. Okay. And this is Fermat's theorem on like really simplified. It's very complex, but we're going to simplify it. So if the function f of x has a relative max or min at like a value, like x equals 2, let's just say, like the c just represents a number, then the derivative will be 0, right? Or does not exist. Because it's not increasing or decreasing at that point. Like you said, Anirudh, it kind of hits that peak, and it's neither going up nor down, it's just kind of stuck there, right? It's static. So what we know is we got to find these critical numbers. Like these are, we call them critical values. So why did we pick 2? Why did we pick, if we look at the other graph, why did we pick, like our critical value here on this graph is that. And that's because there's no slope here. So we're looking at what's happening to the left of that critical value and what's happening to the right of that critical value. Like, so we know on this side that it's increasing because without even graphing it, if all the slopes are positive, I know that the graph is increasing to that relative or relative max or min. And because this side, I know it's decreasing because they are negative. So even without this picture, if I have my critical point and I have some data to the left and to the right of it, I kind of already know the shape without ever having to graph it. And so that's the thing. So we're going to find critical points. So we're determining the critical values. So what we're looking for Or undefined. Like it could be 0 or undefined, depending on what kind of shape we have of our graph. So if we're looking for slope, we know that we're doing the first derivative. So all we're going to do is we're going to find our first derivative. And we're going to set it equal to 0. And we're going to solve. And so in this case, I'm pretty sure I can factor it. You could use the quadratic formula if you wanted as well. So these will be our critical values. And so when we're looking for that number line, we know at -3, the slope is 0, and we know at -1, the slope is 0. So what's happening in between those? We'd have to look at what -4 is doing. We'd have to look at what -2 is doing in between them, or 0, right? We can do 0 really quick. We know that 0, this would be a positive out here, right? If we substituted in a value of 0, this one would be positive. So we know that this would be an increasing from -1. So these two represent either a relative max or a relative min, and we're going to know if it's a min or a max based on what it's doing in between those 2 points.
Just chuck in -2, eh?
What's -2?
In between them.
Yeah. So tell me what it is.
I don't know.
We'll put it in. So that'll be 12. That'll be -24. So that'll be a -12. -12 plus 9. That's going to be negative. So we know it's decreasing in between. And what about -4? Oh, yeah, -4. What about -4? 16 times 3? 48? No. Yeah, 48.
Yeah.
It's positive. So I know stuff about my graph. So if this is positive up into -3, I know my graph's doing this. It hits -3, and then it's going to start going down, right? It's going to go down till it hits -1. Oh, I'm starting to curve up again. Till it hits -1, and then at -1, it's going to start increasing again. So we know at this point, it's a relative max. We don't know if it's an absolute. We know it's a relative max. And we know at this point, it's a relative min. So without ever graphing this equation, we know lots about it. Because I'm not going to classify that as a graph. That's just...
That's what I like.
Right? We haven't graphed a ton, have we? Now that I think of that, yeah, like you did so much graphing in grade 12.
That's really like, I get panic attacks when you graph people now.
Okay, so we're going to do the first level derivative of this, but I can't do it in radical form. So I'm just changing the original function to rational exponents. And then the derivative and so we set the derivative equal to 0 to find our critical point. Well, that's ugly. It's ugly. I'm going to put it back into radical form because I think that will help you see what the problem is.
Oh, so it's just 0 our critical point?
Right, because we know that oh, that's a cube root. Sorry, forgot my index there. So what do we know? We know that, what can x not be?
0.
Right, so there's a non-permissible value here because that is on the denominator. So for our NPVs, we know that x cannot equal 0, just because that would give us an undefined. So what we know is that the slope is undefined at this point because we can't put 0 in there. If we were trying to solve this, we'd multiply both sides, we'd lose an x, there wouldn't be anything to solve for. So in this case, if we put x in there as 0, we know the slope's undefined. Would everybody agree with that? We get that error on our calculator. We've done this a million times with trig graphs, so we know the slope's undefined. So we can safely say that the critical value in this case is 0. I like it much better when it's equal to 0 and I can solve it out. These ones make a little less sense just because you're kind of going on, okay, well, if it's undefined, then my non-permissible value is my critical point, because I'm going to end up with an undefined, which is okay too. Okay.
So what NPV was our critical point in the last?
Yes, like so when you get a situation where it's undefined, it's your NPV that becomes your critical point. We'll just draw an arrow, it'll make it better. All right, first derivative test. Okay, so let C be a critical number, I call them critical values, of a continuous function. Okay, we just figured out how to solve for those. If the derivative changes from positive to negative, in other words, it changes from increasing to decreasing, then it's a relative maximum. It's exactly what we just described here, right? So we're doing that test, positive to negative, we know that we're going to have a maximum. Negative to positive, we're going to have a minimum. Okay, I'm going to grab my highlighter. My orange one seems, so if we're going positive to negative, we're going to be at a relative maximum. And if we go from negative to positive, we're going to be at a relative minimum. If the derivative does not change, if it's like positive, positive, positive all the way across, it's not a relative extreme point. It's not that critical value, okay? So if there's no change, if it does not change, then there's not a relative extreme. It's unlikely that happens, but sometimes it does, so just so you know. Okay, use the first derivative test to determine the relative extremes of this particular function. Step 1, find the derivative and solve for our critical values. Oops. So those are going to be my critical values.
Just taking grade 10.
It's, well, yes, we did have to factor some stuff, right? So it's grade 10 all over again. Slope, It's factoring, like it's just grade 10. Grade 10 prepared you.
This is the best.
All right, so then we put those on our number line. So step 2, I'm going to call it sign analysis because that's really what we're doing. I feel like I missed something there. Okay, so we're going to have a -1. We're going to have a +1, right? So we're going to pick values in between those points to figure out what y is doing. So definitely 0. If we put 0 in here, if we put 0 into the derivative,
-3.
we're at -3, right? So if we pick 0, we know that we're going to be a negative number. If we pick 2, what do we get?
Positive number?
Positive number. And if we pick -2,
Positive?
we also get a positive number. Okay, so what do we know from this?
It's increasing, and then in the mid, once it reaches negative.
So we're increasing, we're going up the mountain, we stop at a relative maximum, and then we start to go down. So we know x equals -1 is a relative maximum. And that's just, again, we're traveling from a positive to a negative, so that's going to be a relative maximum. I don't really remember the rules. I just know, like, I'm thinking, okay, positive, positive, positive. I reach the top of the mountain, and then I'm going to go down. So now you're going down, 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 down. So you're still traveling down here. So we know that x equals +1 is a relative minimum. Okay. Can you give these to me as coordinate pairs? How would we do that? Into the original function. So let's do that. So if we have, oops. So if I ask you to find the coordinates of the relative max and min, you have to go back and sub into that original equation. Does that make sense? Like, it's not hard, but it just takes some thinking and keeping all of this straight. And I think that's the challenge in all of this. Okay, one last example, and then we are done.
Lessons are really small.
They are really small. Use the first derivative test to find the relative extremes, to determine the relative extremes. Okay, so let's go.
Y equals -6x squared?
Yep. So first thing we're going to do is we're going to find our derivative. So -6x squared. Nothing really exciting about that. Next step is we're going to set it equal to 0 and solve. Now, you can do all the math if you want, so we're gonna divide by -6, divide by -6. But if you can see it, just do it. Like I probably would have went from here to this last line, like I wouldn't have shown all the math, because I know there's only one value when I'm multiplying things that will work, and that's 0. All right, so if we were to dump this on a number line, 0's in the middle. I'm going to pick -1. I'm going to pick +1. So it doesn't really matter. Both are going to be negative. So they're both going to be negative at that particular point. Because remember, we're looking, you're like, oh, but that's a parabola. So we would be increasing, we'd be decreasing, but we're not talking about this one. We're talking about this cubic function, right? So even though we're looking at this and it is a parabola, we're looking at how this relates to its cubic function. So sometimes I get caught up in, well, that's not right, because we'd be increasing to 0 and then decreasing after 0. That's true of this, but this stuff is related to the cubic graph. So what we know here, if there's no change, what do we know? There's no relative max or min. And what do we know about that graph? We know that it's going to start in 2 and end in 4. What do we know about all those y values? They're going to keep on decreasing. They're just going to keep going, right? So we might find that this is similar to a straight line. There's no relative max or min at x equals 0. And we would say the function is decreasing on the domain. And this is the weird part. If there's no change, you should just be able to say, oh, sorry, you guys can't see that. Positive infinity to negative infinity and call it done. But because we've identified 0 as a critical value, it's kind of like a floating point, like it's neither increasing nor decreasing. So we have to list it as an exclusion point because we've identified it as a critical value. So that's that, and that's how we determine local max and mins on polynomial graphs. It's just, I can't teach you this part of it without going into what a derivative is, and that's going to take too long, and the grade 12 course is already pretty packed, and it's not a requirement to know, but this is how you calculate them. Ta-da! We're done.